here we go. So this is Tuesday in your world. Still Saturday in my world. It is now 5 after 12, an hour later. So now we're going to move on to day 2 of the lab. Okay, so here's what's going to happen in part 2. By now, hopefully you should have your value of K. All right, that's going to be important. At this point, you should have your value of K. You should see that it's first order with respect to acetone, first order with respect to the hydrochloric acid, 0 order with respect to the iodine. Now, what you're going to do on part 5, okay, this is the predictive nature. We're going to see if this actually works. So what you're going to do, and you have to have some of each, what you're going to do is that you are going to pick a different set of volumes from the first 4, okay, completely different set. You pick them. So you're going to have volume of acetone, iodine, hydrochloric acid, and water, so that the total volume still adds up to 50. You're going to pick these. I'm not there. I'm in DC at the moment. So you're going to pick your own set of values, and then, and listen to me, because everybody's groups are going to be different, okay? Leslie's is going to be different from Aspen's, which is going to be different from Peyton's, okay? Everybody's volumes are going to be different. So show me the calculations of the initial concentrations after they were mixed. Again, you're just going to use M1V1 equals M2V2. So you're going to show me the concentrations of the acetone, the I2, and the hydronium ions after they have been mixed. Now here's the next thing. Then over on page 6, what you're going to do is you are going to plug those numbers into R equals K concentration of your acetone, concentration of your hydronium ions, okay? Since you know the K value, you are going to calculate the rate. Listen to me, this side of the room in particular. Everybody's numbers are different. Show me the calculation of the rate. Put in the numbers. Then, knowing the rate and knowing the initial concentration of the iodine, you're going to predict a time. Okay? You're going to say, okay, this is how long this thing should take. Because remember, if you work backwards, your rate was the change in concentration of the iodine over time. Now you're going to know what the rate is. You're going to have that value. You're going to know the concentration of your iodine. Boom. You're going to solve for time. Show me the calculation. Right side of the room. That's actually true of everybody, but I want to emphasize this thing. Because again, when I get back on Wednesday, I should be able to look and go, hey, Zach, Skippy, how did you get your time? Okay, because if that time just magically shows up, bad things are going to happen. Now, choose wisely in terms of the time, okay, in terms of your concentrations to determine the time, okay? Just giving you a hint. Look at what could potentially make that reaction go faster, what could make it go slower. Just don't randomly pick things, okay? Look at that. Do we want this reaction to take place quickly? Do we want this to take a while? Okay. Then it says, teacher signature, Ms. Calhoun, you're going to sign off on this, okay? Go up to them, have the kids sign off on it, say, hey, this is what you're, and make sure that you're seeing these calculations. And then you're going to run the reaction, and you're going to see how close your reaction happens. And it's the exact same process. Mix together the water, the acetone, and the hydrochloric acid. Add the iodine, start your stopwatches, observe what happens. There you go. Okay, now we're going to determine the activation energy, okay? You're going to choose one of the reaction mixtures. I don't care which one, okay? 1, 2, 3, or 4. You're going to pick one. I don't care which one. You're going to pick one. And now we're going to look at what's going to happen in terms of an influence of temperature. So this is important in terms of the technique. So you already have the room temperature 1. You already have the data. Don't need to do that one again. If you want to, you can. If you really want to get scientifically bougie, we'll go back to bougie word again. I don't know why that struck me as funny today. But if you want to do it scientifically bougie, you should run that reaction again, or you can just use your data. It's just how bougie you want to get. Now, so you're going to tell me which reaction are you going to use. 1, 2, 3, or 4. Okay? I don't care. Pick one. So you're going to run the reaction at about 10 degrees Celsius, and then you're going to run it at about 40 degrees Celsius. Now, here's what has to happen. I would run the 10-degree one first, because that's the cold temperature one, and that's going to take the longest. So what you want to do, listen to me. In a small beaker, mix together whatever reaction that you chose, mix together the water, the acetone. Oh, I hate my pen. The acetone and the acid. Mix together that. In a test tube, have your iodine by itself. So in an ice bath, okay, Morella, make sure you have the ice out from the freezer. You'd have an ice bath, and you're going to put these in there separately. Do not combine them. Do not combine them. So you want to put them in there, take the OGT, and measure the temperature of both of those until it gets down to about 10 degrees, okay? Because you don't want to mix them together and then cool them down. You want to cool them down till they're about 10 degrees. Then add the iodine to it, okay? Then you can start your timer. Now, because of the fact that we're having an ambient temperature of about 20 degrees inside that room, depending upon how long this reaction takes, you want to monitor the temperature of the reaction, okay? And if that begins to warm up, you might have to put that back in the water bath again to chill it back down to about 10 degrees. So, and literally, this might take you a while, okay? And like, when I did mine, it took about 5 minutes for it to run, okay? So, it might take a while. That's why you want to run the cold one first. So, run this one, get it up and going, because that's going to take a while. You got to get it cooled down, and like I said, if it runs too long, you might have to put it back in the ice bath to cool that reaction back down to 10 degrees. Okay, you're going to have your room temperature one. Then you're going to do a hot bath. So then you're going to get out your hot plates, set up a water bath, and you're going to do the same process. You're going to have your acetone, water, hydrogen in one, have the iodine by itself, warm that up to it's about 40, okay? I don't want to go fast, higher than about 40 degrees. Now, then you're going to have that together, boom. Now, this reaction is going to happen really, really quick. Like, when I did mine, it took about 20 seconds. So you're not going to have time to pour it in and then separate it out into the different test tubes. You're just going to pour it in, boom, start the stopwatch, boom, there you go. So, here's what you're going to have. Depending upon which reaction that you took, you're going to have R equaling K, concentration of your acetone, concentration of your hydronium ions, okay? So here's what you're going to have to do. You're going to know the temperature in Kelvin. You're going to have to calculate the rate, because you're going to know the time, and you're going to know the change in concentration of the iodine. So you're going to have that rate. You're going to know the concentrations of these. You're going to calculate the value of K. So you're going to have 3 different values of K. So the graph that you're going to draw, and this is how we're going to go after the activation energy. This is the only graph that you're going to have to draw. Chill out, okay? You only have to draw one graph. Okay. So you take the natural log of K, and then over here you're going to have 1 over temperature in Kelvin, okay? And this graph should get, when you get done, look something like this. You're going to have 3 points. Draw the line of best fit. Circle the points on the graph that you're going to use to actually find that point. Show me the calculation of that slope. The units are going to be Kelvin, but it isn't the actual temperature. That's the weird deal. The slope is Kelvin, but it isn't the temperature because the temperature is changing. So when you get down to this graph, it's going to look something like this. And then you're going to use the fact that I have no idea what's wrong with my pen today. Maybe because it's Saturday. You're going to use negative E sub A over R equals slope. Skippy. Make sure that you're using the R value of 8.314 joules per mole Kelvin. So that way when you multiply that slope by Kelvin, the Kelvins cancel out, you get units of joules. That's what activation energy is equal to. So to give you some ballpark, and again, this is wide variance, okay? Depending upon which points, because you only have 3 points on your slope, you can get very different values, but as a reference, when I did my data, I got my value of my slope to be something times 10 to the 4th Kelvin. That's what I got for the slope of my line. And like I said, there could be huge variances in this. Now, if you get 10 to the 8th, something's wrong. And then my activation energy, I got 10 to the 5th joules. Okay, that gives you some ballpark. Okay, I'm done. You have the rest of this time to work. This lab is going to be due tomorrow. Obviously, I'll be back, hopefully tomorrow. And we'll get through this. Go lab. Be free.